Right, great. Let's start. As I said, good morning. Thanks for joining our webinar. This is going to be the last one before our short summer break. And today's general topic is upscaling and optimization of large area solar cells and LEDs. And we are glad to have here two great speakers. There is Dr. Burwell from Swansea University and Ennio Comi from the ZHAW in Switzerland. Thanks a lot, Gregory and Ennio.
Good morning.
Our first speaker, Gregory, is a lecturer at Swansea University. He specialized in optoelectronics materials and device characterizations. Gregory holds a PhD in nanotechnology from Swansea University and has worked as a senior R&D engineer for different companies in the UK and Spain. His current research involves scaling up optoelectronic devices and developing thin film deposition techniques for PVs and LEDs. The title of Greg talks is Optimization of Large Area Photovoltaics and LEDs. And from my side, that's all. Thanks, Greg, and the floor is yours.
Thank you very much for the introduction. I'll start to share my screen now. Is that okay? Can everyone see? Right, good morning, everyone. I'd like to talk a little bit about optimization of large area photovoltaics and LEDs. Thank you for the introduction. I'm Greg Burwell from the Department of Physics at Swansea University, and I work at the newly opened Centre for Integrative Semiconductor Materials, CISM, at our New Bay campus in Swansea. Anyone who has any questions after, feel free to email me, g.burwell@swansea.ac.uk. So some of the things I want to talk about, first of all, a little bit of our work on large area OLED devices. And as a result of one of our program grants around photovoltaics, looking at some different applications of PV, and I'd like to highlight some of the differences of solar PV versus indoor PV, and how that relates to the scaling of the shunt and series resistances, and then a little bit about how we might learn some lessons about module design for different applications. So we'll start with large area OLED devices, and most of this work you can find in this paper from Advanced Electronic Materials from 2020. So a little bit of background about why we might be interested in optimizing the TCE. So the TCE contribution to embodied energies in different types of solution processed optoelectronic devices, the TCE can be a significant component of the overall embodied energy. So if we want to make photovoltaics or LED systems with low embodied energy to justify why we might use them in net zero goals, we want to understand all the components of that device, not just the active layer. So the TCE, which is predominant in most devices, is ITO or FTO, and that can account for almost 40% of the embodied energy in that device. In addition, the element indium is not very abundant on the Earth, and it's very energy intensive to mine. So this is what's motivating some of the explorations into alternative TCE materials, or TCOs, transparent conductive oxides, that could replace ITO with low embodied energy. One of the ways we're looking at doing this, rather than using a single TCO material, is to combine maybe a lower performance TCO with a metallic grid structure. So at our facility, we can fabricate these grid structures using photolithography, etch and lift-off processes. And with these, we can achieve an equivalent sheet resistance of sub-ohm per square, while maintaining high average visible transmittance above 80%. So we can make these with ITO or other TCOs. One of the interesting things about the metallic grid approach, it's very agnostic as to the TCO material you use, or in fact, you might not use a TCO at all. You might consider using something like a conductive polymer. So in the citation below, we explore some of the parameterization of how you might use metallic grid structures with TCEs. And this is real data from different types of metallic grid structures that were fabricated at our facility. So we measure the optical and electronic properties of these. So what we track here, the figure of merit would be the geometric fill factor or the fraction unshadowed, and we can do that by designing the lithographic structures on the substrate. And with that, then we can also change the grid thickness, so the in-plane thickness of the metallic grid, and achieve an equivalent sheet resistance, which is not obtainable using a single bulk TCO material. One thing we've been looking at doing is using this in combination with aluminium doped zinc oxide, and in particular AZO that's been deposited at low temperatures, so towards low embodied energy systems. We can deposit this material below 100 degrees. Of course, it's indium free, it just has aluminium, zinc, and oxygen. By itself, we get a sheet resistance of around 200 ohm per square, although we have seen some examples that are lower than that. We still get a very good average visible transmittance, about 83%. However, if we combine AZO with metallic grids, we can achieve sub-ohm per square and still very high AVTs. So this is done with an ALD type process. This is another round of work that we'll be publishing in the coming months. So I'd like to highlight some of the uses of Fluxim's tool LAOS when we're simulating OLED structures. So we were trying to make large area OLEDs that might be useful for things like lighting applications. So panel A here shows a typical exploded view of an OLED structure, where you'd have a transparent conductive electrode, you'd have an emissive layer, and then a top electrode. Of course, you might have different transport layers in between those. And one of the things that LAOS lets us to do quite easily is to simulate metallic grid structures on that transparent conductive electrode, and then look at the properties, the overall electronic properties of the device as we scale its area. So in this work, we were looking at comparing 1x1 and 5x5 OLEDs with and without metallic grids. So the abbreviation here, the ITO OLED uses just ITO on its own, and MG OLED is a metallic grid OLED, which uses ITO with a metallic grid. So using LAOS, we could map out the surface potential and then the current density going through the OLED device, and then look at different coupling laws, which represents different thickness of the OLED structures. So one interesting thing we found in this work, if we were to look at simulating thick OLED structures that may be a bit thicker than optimal, but might be relevant for large area processing applications, for example. One thing that was very interesting that came out of this work was the heat that was generated in the OLED, and in particular, the contribution to the heat generated within the OLED in a large area system attributed to the resistance in the transparent electrode. So the higher you have the resistive losses in the transparent electrode, the more joule heating you have at that interface. And therefore, if you have a system that's being driven very hard, like an OLED, you might not have sufficient thermal dissipation to get rid of that heat. So we used the thermal module within LAOS here to simulate the temperature profile across the device and comparing different thicknesses of OLED structures. And what we found here in simulation, that a thick OLED structure without metallic grids could achieve unacceptably high operational temperatures under certain conditions, whereas if you lower the sheet resistance using metallic grid, you can achieve much more reasonable operational temperatures. And this is backed up by real data, so we made very similar structures to the ones we simulated. And what I've got here in panel B is the change in EQE after subsequent measurements, the delta EQE. And what we can see here using the metallic grids, that the delta EQE is very low, close to 0. So the actual performance, the emissive performance of the device doesn't change much with subsequent measurements. However, if we keep measuring device without metallic grids, just a large area ITO-based OLED, then you can see a big change in the EQE LED with subsequent measurements. And using the tool from LAOS, we understand that now that's joule heating within the device that's contributing to the degradation of the system. So the next thing I'd like to look at is photovoltaic devices, both solar PV and indoor. And a lot of this work comes from this citation here, scaling considerations of photovoltaics for indoor applications from Solar RL. And One thing that's interesting to note is the light intensity dependence of the scaling behavior. So we can define this figure of merit, S, which is the ratio of the power densities of a large area and a small area device. And we can approximate what happens under 1 sun conditions and compare that to a 1% sun conditions. And we can track with different sheet resistances in that device at what point do we get 10% or 5% losses as we go to larger characteristic size, the side length of the device. And what we can see, which is somewhat intuitive, at higher radiances, closer to 1 sun conditions, you can only afford a smaller device. However, if you scale that up with lower radiance, with 1% sun, you can make much larger devices without suffering the same series resistor loss. One thing we've been doing recently is to try and come up with a nice figure of merit for the TCE in thin film solar cells. And you can see on the contour plot here, what we've been doing is surveying different TCE technologies, different materials, such as ITO, such as metallic nanowires, and trying to compare these with these analytical models that we are about to publish. And it's an example of a real structure that we've made with a metallic grid here. So you can see on this plot that our AZO gridded TCE outperforms most monolithic systems when you get to larger areas. But to get into a bit more detail, we need to understand how the shunt and the series resistances scale in a device. So we can get a lot of insight from equivalent circuit models, and they provide insight into the various loss mechanisms with varying light intensities. So if we use a 2-diode model, for example, an OPV device, we can track the contribution from the CT states, and this is labeled diode 1, and a contribution from the trap states in diode 2. We can simulate different thicknesses using this, but also what we can do is start to build a model of combining this with shunt and series elements to see what happens at different light intensities. And if you want to look into more detail here, there's a nice paper from Nassim Zarabi about using these equivalent circuit models for modeling mid-gap trap states. So one thing that's very important to note as you go to lower irradiances, that the shunt resistance becomes increasingly important. So we can simulate a similar type of device, but we will change the shunt resistance in that equivalent circuit model. And you can see here, for example, we've just plotted the 500 lux point on the dashed line, that if you have a shunt resistance that is too low, you just cannot generate much power out of that device. So we need to understand then that as you go to lower radiances, for example, for indoor photovoltaics, it's not so much the series resistance in the TC that starts to matter, but it's the shunt resistance, or the specific shunt resistance, to be more specific, that matters when you want to understand how that's going to perform at low light conditions. So one thing I've been interested in trying to understand is physically, how does the specific shunt resistance scale as a function of size when you change different parameters of a device? So in panels A and B, we can see some data from real systems that were fabricated with different active layer thicknesses. This is a PM6Y6 and PM6BTP-EC9 devices. And we can track the average shunt resistance from a batch of devices. And you can see intuitively that the thicker the active layer thickness, then the higher the specific shunt resistance of that device. And here's a specific model in panel C and D that try to explain some of that. So this is a probability density function, which is trying to model what are the odds of, what's the probability of getting a catastrophic shunt, namely one that shorts between the top and the bottom electrodes, as a function of active layer thickness. So this is based on a log normal distribution, and basically saying that the thicker the active layer thickness, then the lower the probability you have of having a catastrophic shunt. So therefore, we can get a similar cut time of trend that we get with active layer thickness in panel A and B. So that's in the dimension of the active layer of the device. Panel D then is a cumulative density function as we extrapolate to X and Y dimensions across the device. So as that cell size becomes larger, what's the cumulative probability of getting a catastrophic shunt for a given system? And that, of course, assumes a lot of things regarding the fabrication considerations of that device. But as you get larger, the odds of having a catastrophic shunt therefore starts to increase as well. So there's two things to consider. One is the active layer thickness and also the lateral dimensions of the device as well. So one thing that the nice chaps at Fluxim did for us is they added a feature to Laos that allows us to add random defects to a large area device. And here's two basic models to show more intuitive understanding of how that works. So if we fix capital N, which is the number of defects on a device, and then we can vary lowercase n, which is the number density and the area, then if we fix the number of defects and just make it larger, then the specific shunt resistance increases, and therefore we get an increase in fill factor. However, we do the opposite. If we fix the number density and vary the number, then the specific shunt resistance is flat. And I just wanted to highlight this to really elucidate the difference between the shunt resistance that you'd measure from an SMU if you were to plug your device in versus the specific shunt resistance in units ohm centimeter squared. So we have to consider area, namely ohm centimeter squared, when we're modeling how that device is going to behave as a function of scale. So here's some other models we've been looking at using Laos. We've been looking at using a basic probability density function, which is a simple exponential, to try and capture some of the style of behavior you might see as you were to go to larger area devices. So the larger the area device, if the probability of getting a defect scales with the exponential of the side length, then of course you're going to get more defects in that device as a function of area. We can then simulate things under different irradiances by changing the coupling law within Laos, and then seeing what happens if we combine these random defects with the metallic grids I mentioned earlier. So we're very much interested in understanding, trying to capture some of that behavior of a real-world fabricated device and trying to play with some of the parameters around the TCE to try and understand how we can best optimize that. And that brings me to a little bit on module design. So we're very interested in using indoor photovoltaics to power things like IoT devices, like sensor nodes, and to achieve an acceptable voltage for energy harvesting, you would typically assemble these into modules, which will have a number of cells. And this, of course, is the typical way you would connect those together with the P1, P2, and P3 regions. And one thing we've been trying to predict using tools like Laos is to look at the overall system efficiency. So not just the photovoltaic efficiency of an indoor PV module, which comprises of a number of cells in series, but given the voltage output of that device, what's the coupling efficiency into the energy harvesting circuit? And then how does that vary as we vary parameters such as the number of cells in that device? So that's a manuscript in preparation we'd be hoping to publish in the coming months. So to wrap up then, a couple of conclusions. So on OLEDs, monitoring the equivalent sheet resistance to your TC is very important, and metallic grids are a great way of lowering that sheet resistance. PV materials can be optimized for specific applications such as solar and indoor use. When you look at indoor cells, the shunt resistance can have its own scaling behavior, and modeling these as point defects can help us understand some of the emergent properties of that. And then these can be translated into application-specific module designs. Thank you very much.
Thanks a lot, Gregory. That was
Thank you.
great. There are already some questions, but let's keep them after Ennio's talk. I'm sure there is going to be time for question for both Ennio and you. Let me introduce Ennio. He's a researcher at the ZHAW School of Engineering here in Winterthur in Switzerland. He's specialized in organic electronics and photovoltaics. Ennio has a master's degree in organic electronics and photovoltaics, and is interested in developing advanced simulation and measurement technology to accelerate the upscaling of perovskite solar cells. Ennio's talk is special effect in carbon-based HTM-free perovskite solar cells. And we are very pleased to have Ennio here. Please, Ennio, you can start.
Thanks a lot, Davide, for the nice introduction. Hello, everyone. And thanks also for the opportunity to talk about the spatial effects that we see in carbon-based perovskite solar cells. So for perovskite solar cells to be successful on the market, they not only need to be stable, cheap, and efficient, but they also have to be upscaled to larger areas. And lots of efforts have been made towards that direction in the last few years. You see that in this graph in the middle, that lots of larger area modules and cells have been produced, and they're getting slightly also more efficient with time. But in the end, we have to say that with larger areas in general, the efficiency drops significantly. And that's especially the case for perovskite solar cells compared to other technologies. And one reason for that, of course, is the resistances that are increasing with larger areas. Also, dead areas increase with interconnections from modules. But a huge factor to this efficiency drop is our inhomogeneous layers. And one way to analyze the homogeneity of thin film layers are imaging techniques. And lately, we're working a lot with imaging techniques in our lab. And here I brought you a few of those spatial effects that we see in perovskite solar cells with different imaging techniques. So on the left, you see those typical shunts and hotspots. They're usually measured with lock-in thermography methods. We are also looking at degradation patterns here in this module with a PL image. Then we sometimes see some comet-like features, and they're coming from unwanted particles originating from spin-coated devices, these comet-like features. Especially in screen-printed devices, there can be some grid patterns can appear where too much pressure is applied, bright spots, cracks, also these very horizontal lines, very straight lines that can come from inkjet printing. And of course, we also see lots of small dark spots. And then always the question is, how harmful are all these features, and how can we then improve fabrication processes to increase the efficiency of those devices? And today I want to talk about some of those spatial effects that we saw in perovskite solar cells and how we combine these imaging techniques with simulations to learn a bit more about those features. First, I want to talk about a study with lock-in thermography where we used LAWs to model a defect, then electroluminescence imaging. Here we used ZHAWs and LAWs. And in the end, I want to talk about an interesting technique that uses PL imaging to look at local charge extraction in devices. We're working a lot with Solaronics, a company based in the western part of Switzerland that produces carbon-based perovskite solar cells by screen and inkjet printing. And those are mesoporous devices with a mesoporous titania and zirconia layer. And they have a thick carbon electrode on top, and the perovskite is infiltrated. After the stack is finished, the perovskite is infiltrated through these mesoporous layers. I'm mostly showing mid-area devices like these 1.2 square centimeter devices. Then there are some images of dual cells. They're quite interesting to study interconnections. And we also got some modules from Solaronics. Those devices are not very efficient with around 12% PCE, but they're quite stable and reproducible. And But first, I would like to start with a little introduction into LAWs. We have already heard a bit about the electrical and thermal mode of LAWs. LAWs is a 2D plus 1D FEM tool, and it solves 2D equations on 2D top and bottom electrodes, and these electrodes are connected with a vertical 1D coupling law. And this coupling law just describes the stack of the device that we want to simulate, or a defect that we can add, for example. This could be a JV characteristic. So LAWS has an electrical mode where we can simulate potential distributions, all influenced by the sheet resistance, for example. That gets quite important when we're talking about larger areas. Can add grid lines, that's what we already heard from Gregory's talk. Also mentioned the thermal mode in LAWS. Here we can use the currents that have been calculated by the electrical mode to calculate Joule heating and the temperature distribution on areas. So these are the steady state modes or DC modes. LAWS also has an AC mode. Here for the electrical part, this could help to study or look at the influence that large areas or shunts can have on impedance spectroscopy data. But more interesting maybe for today is the thermal AC mode of LAWS. Here we can look at the influence that the small signal perturbation around the bias potential has on the temperature of the device. And that brings me to the next topic, lock-in thermography imaging methods. So lock-in thermography is quite famous for imaging of small defects with very little heating due to a very high signal-to-noise ratio. And that high signal-to-noise ratio is achieved because the heating is induced periodically, and that suppresses lateral heat diffusion. The lock-in algorithm for the imaging technique uses a series of images that depends on the frame rate of the infrared camera. Then these images are Fourier transformed based on the modulation frequency. In our case, we're working with 1 Hertz. And from that Fourier transformed images, we get real and an imaginary image that allows to calculate an amplitude and a phase. And two very famous lock-in thermography methods are dark lock-in thermography and ELIT, illuminated lock-in thermography. In DLIT, voltage, usually a rectangular voltage signal, is applied to the device to trigger the heating, and in ELIT, light pulses are used. A method that's not very famous yet is small signal dark lock-in thermography. This is a method that can be very well simulated in LAWS, and we think this method is also especially beneficial for perovskite solar cells, where ions can influence the measurement results substantially. Because in SSD-LIT, we apply a small signal perturbation around the bias potential, and this bias potential is causing kind of a preconditioning to the device. And this can be very important to image diode-like shunts. We can see this in this image right here. We have the dark lock-in thermography image of a device, and we see a very pronounced shunt, a very pronounced hotspot. This probably has an ohmic nature. And if we measure the same device with the SSD-LIT method in the same voltage range, we still see this shunt, but we see some heating on the active area as well, because we're kind of in a quasi-steady state. And we see some little hotspots that appear as well, and those are probably have a diode-like nature. And we used SSD-LIT as well to measure or to model a shunt that we measured in a perovskite solar cell. So we applied various bias potentials and did as an SSD-LIT measurement. We wanted to remodel this defect that we see. And we first started by using an ohmic coupling law in LAWS, and then we immediately saw that it was impossible to to get the same behavior in the simulation as we saw in the measurement, because in the measurement, the temperature on the spot just started to increase and then dropped again, while on the active area, the temperature just increased steadily. And yeah, it was impossible to model this with an ohmic defect, so we used a diode-like defect, and then this the simulation results became much more similar to the measurement. We had a first increase and then a drop in potential in temperature. What you see down here is an electroluminescence image of the same cell. Around this hotspot, there is a little dark area. And on the right is the simulated EL image. And also allows to simulate electroluminescence images because EL images are proportional to the local junction voltage. And that's what we get from the electrical mode in LAWs. We also see that here the potential also drops around this modeled defect. I want to continue with electroluminescence images. So we measured a few different devices. The device here on the left has a very well-conducting top electrode and a quite resistive bottom electrode. And that's why we see the signal just fading from a very bright signal here on the bottom to a very dark signal here on top. It's also what we can simulate very well. And the carbon devices, mesoporous devices that we're working with, they have two resistive electrodes on the top and bottom, and that's why we have this very bright signal on top, a darker signal in the center, and again, the signal increases again on the bottom. And those simulations that you see here are just the potential difference between top and bottom electrode. The same is also for silicon solar cells. Silicon solar cells have a very resistive top electrode. That's why they have those fingers. Here you see an simulated, an EL image of a silicon solar cell with a shunt and the simulated EL image in LAWs. And as you can see here, the potential drops between the grid lines quite substantially, even though they are very narrowly spaced, and around the defect, the potential drops as well. So EL images can deliver a lot of information about the resistive electrodes. And all those simulations that I've shown you were all in steady state, and also the measurements we assume, but usually what we see when we apply a voltage in the dark and measure the EL signal of those devices are quite interesting transients. They look kind of like this. So when we apply the voltage, we see a very steep increase in the EL signal, and at a certain point it tops out and then the signal drops again. This happens while the wavelength, the peak wavelength, just stays constant and the current increases steadily. We thought that was quite interesting. And something else that we saw were very bright spots in some devices. So in some devices, these bright spots appeared very early, and then the kind of the active area started to pick up with time, and then those spots disappeared after some time. And yeah, we wanted to find out more about this. So we had these two behaviors, bright spots that appeared earlier and have a very strong EL signal, and the active area that also has a peak at a certain point and then the signal drops again. And to understand this a bit better, we modeled the device in ZHAW, the 1D drift diffusion solver from Fluxim. We modeled this device including anions, cations, and traps. And for the desired electroluminescent signal that we wanted to simulate, we used a Langevin recombination coupled emission model. And we saw quite early that we were able to mimic this behavior in ZHAW, that you see this increase in EL signal and then signal drops again. But we had to use quite a high ion density. So this just happened if the ion density was high enough. And another interesting parameter was the cation mobility. The cations in our case were the more mobile ionic species. And from the cation mobility, we were able to fix the timing of this first peak that in our case happened around after about 40 seconds. And yeah, with those two parameters, it was quite well possible to mimic this behavior on the active area. But for the bright spots, we just had to double the ion density. And that caused the simulation to increase the EL signal and put this first peak at an earlier point in time. So probably in these bright spots, there were cavities in the mesoporous structure where the perovskite then crystallized more freely compared to the mesoporous structure. And something else that this simulation predicted was that if we have two ion species, a faster one and a slower one, the slower ion species can cause a late increase after the EL signal has dropped. So we measured again here in that case for an hour, and we saw that this first peak happened, the signal dropped, and then actually the EL signal started to increase again. Here after an hour, it even surpassed this first peak, while the current continuously dropped. So that was quite interesting that the simulation just predicted that. Then we played around a bit with those ZHAW simulations. We have 1D ZHAW simulations, and we can use those as coupling laws for law simulations. From ZHAWs, we exported JVLs, voltage-dependent current density and luminance characteristics in 3 different points in time. And then we added a subdomain in the center in laws to mimic this bright spot, and we put the coupling law on the active area, and that's how we were able to simulate kind of transient 2D luminance simulations. And those images or these simulations are also affected by the potential drop. So we see how the potential on the active area also influences the luminance. Now, this is the last topic from my side, the delta PL measurement method. This is a method to look qualitatively, at least, at local charge extraction of devices. For that method, we need 2 PL images, one at VOC and one at short circuit. At VOC, we are not extracting any charge carriers, and that's why we have a very high amount of radiative recombination, what you see in this image. And at short circuit, the PL signal should be quenched as we are extracting a lot of charge carriers. And if we subtract those 2 images, we get the images here on the right, these delta PL images that can be proportional to the local charge extraction. Actually, I don't know where this circle in the center comes from. Maybe it comes from the encapsulation process. This was an encapsulated device. But what we see is that here on the edges, we have quite high charge extraction. That's probably due to some thickness variations on the edges that are quite common. And what we see as well, maybe you remember the grid patterns that I mentioned in the beginning of the talk. Here we see that probably these grid patterns and too much pressure during the screen printing process is not very beneficial for the devices. And what we also have to be aware of in these measurements are always the transients. Here we see a very similar behavior in the PL signal at VOC with an increase and then it drops. So we have to be aware of this. But something interesting that the transients also can show is our charge extraction barriers that can form over time, which we see here. It's from a publication. We see how the signal at short circuit then can increase over time, and we have also seen this as well in some of our devices. To summarize, I've shown you some of the spatial effects that we see and how we use simulations to better understand those. And yeah, we can really, simulations can really help to understand those images and also the transience effects, especially in perovskite solar cells. What I also want to mention is that a combination of different imaging techniques can help to fully understand or to understand the devices a bit better. For example, with PL and EL images, we cannot look at the interconnection properly, but with lock-in thermography, we can detect also heating in the interconnection very well if there are some problems. And to conclude, a little outlook, we want to investigate the degradation also with imaging techniques. So with damp heat cycles, we want to see where the devices degrade and why, find out why. Also look at different encapsulation materials. Yeah. And modules are always a bit puzzling. They have very interesting transients, and I also think that simulations can help, especially LAWS simulations. LAWS is very well capable of simulating modules, and yeah, we want to look a bit further into this. We are also developing an imaging measurement tool, prototype at the moment, that incorporates all the imaging techniques and more that I've mentioned today. And yeah, that's also continuous work. And thanks a lot for your kind attention. I want to thank everyone that collaborated in this work, and also the funding is highly appreciated. Thanks a lot.
Thanks a lot, Ennio. It was great. Now, there are some questions, and I would like to start with Gregory.
Sure
They're
thing.
asking you, what are the specific type of defects that we're simulating in order to see the relationship between the shunt resistance and the device area?
Okay, so simulation-wise, what we assume is an ohmic area on that device. So we assume that they have a direct short between the top and bottom electrodes. So that's ohmic behavior with a given resistance. Physically, what that means is a much more complicated question, and we saw some things that alluded to this just in the talk just gone. So there's two different ways of thinking about that question. One is what can we simulate in terms of how does that defect behave electrically, versus how do we physically understand that source of defect? Is that something from fabrication? Is that some sort of extrinsic impurity in the solution before we've put that down with spin coating or blade coating? Or is that some intrinsic thing that's happening in the film? I think that's something that we need to understand a lot more of. I assume both of those things are happening when we scale those things.
Yeah.
So I hope that answers your question.
I have a simple question myself. You have been showing an honeycomb electrode. Did you try also some other structures, fingers, anything
We
else?
have tried, yeah. So we have done some comparisons. We find, due to the geometric packing, that the honeycomb is usually the most efficient to use. That's why we tend to stick with that now, and that's what we fabricate in real life. It's a nice thing about using a lithographic-based technique is we can have any shape we want, basically. So we can do more complicated structures like honeycomb as opposed to just doing rectangular grids.
Great. Now, Ennio, there are a couple of suggestions and questions for you. The first one is they're saying that possibly the circle that you have been showing in one of the last slides comes to from the spin coating, and the same is for the different PL data at the corners. It's more a suggestion for you.
Yeah, no, these devices have not been spin coated. The Perovskite has been infiltrated in that device with an inkjet printer. Some devices from Solaronics also had this circular feature in the center that came from drop cast deposition of the Perovskite. But that was not the case in that device. So yeah, that's a very interesting feature there, and maybe it really comes from the encapsulation process.
Yeah. There's another question for you, Ennio. Do you find that electroluminescence measurement cause a degradation to the device, particularly in the modules?
Yeah, it's in many devices that are not very emissive. Sometimes we have to apply quite a high voltage, voltage higher than the VOC, to get a good image. So this could cause some damage, but usually these measurements are quite quickly done in a matter of a few seconds if there are not huge transients. So yeah, this shouldn't be very harmful for the devices. And we've done also a few tests where we did a sequence of different imaging methods. We applied voltages and so on, also pulsed voltages, and these devices didn't really seem to degrade from that very strongly.
This one is for you, Gregory. Is the honeycomb electrode fabrication scalable? And do you think this is suitable for a mass production of these devices?
Yeah, that's a very good question. So, of course, if we're doing that in a university R&D facility, we can kind of make what we want, and we can use more time-intensive techniques. But that is a valid point to say, as you scale these up, and I guess the point being you want OLEDs, OPV, or the perovskite alternatives to be low cost. It might not be. So it very much depends on the fabrication methods of making that structure. If you need something that can only write in straight lines, like an inkjet or something like this, then perhaps not. And then you're thinking about things like registration problems and stuff like that if you have to do multiple layers. So yeah, it is a valid point. It's something we are thinking about. How do we make more complex grid structures using more scalable techniques?
Yeah. And then I have a couple of questions for you as well. You have been showing this specific feature, the electroluminescence increases when the voltage is applied. Do you see a continuous increase of the EL, or somehow there is a plateau? And the other question is the VOC of the solar cell. What does it do?
I am. Yeah, we applied voltage for a very long time to those devices, and we saw that the EL just continued to increase for hours and hours. So in few devices, the EL just reached the top at about 8 hours. After about 8 hours, and then also the current stopped dropping, and yeah, we saw after 8 hours that's kind of topped out. And then the other question was about VOC. Yes, while the EL signal increases, also the VOC increases at the same time. Yeah. So yeah, this behaves very similarly.
And regarding the thermal simulation, the AC thermal that you have been showing, you have been saying that there is a coupling law. But was this a measured coupling law, or you simulated that?
Well, for the electrical simulation, we measured a coupling law. There we used the JV characteristic that we cleared of any series resistances, because the series resistances should come from the 2D electrodes in Laos. And for the AC coupling law, we used an RC element. But we could have also used a ZHAW simulation, for example, or measure impedance spectra of ideally a small device over several voltages and in a large frequency range. Yeah, it could be used as a coupling law.
I see here there is another question. Does the band gap of the material affect the efficiency? Example, I'm not sure how to read this. Probably they're asking if the properties of the materials are affecting the efficiency of the solar cells. I guess yes. Yeah. If I don't see any other questions, so I would like to thank you both. It was a great webinar. The next one that we are going to do is going to be after the summer. As I said, it's set for September the 9th. It's a Monday at 10 a.m. We are going to have Thorsten Bremer from Wave Labs. He's going to explain us how LED solar simulator works, and Antonio Cabas-Vidania from Fluxim is focusing on stability of perovskite solar cells. So I would like to thank you both. Thanks everyone for this webinar, and I will see you the next time. Bye.
Thanks a lot.
Thank you. See you soon.
Bye-bye.
Bye.